Okay, today you're in for a treat, and you're in for the treat of class ending early because so um, this is a lecture that's normally taught by Professor Black, and so I assumed that Professor Black was going to teach it, but it turns out he's in a different country, so-called Austria, he claims. And I didn't know this. I didn't find out until I pinged him, until I called him this morning. So I'm using his slides, which I don't know very well. There are not very many of them, and um, in other words, I ask for your indulgence, and I think we will finish early. So you'll have more time to go and work on homework 2. How is homework 2 going? Who here is done with homework 2? More than I thought. Who here has made a lot of progress on homework 2? Who here hasn't started homework 2? Hopefully no one. Otherwise, you're in deep, deep trouble. If you haven't started, you might consider dropping homework 2. But not the whole class, because we want you to stay in the class. This is actually the hardest of the homeworks in a lot of ways. So if you make it through this, then you can make it through anything in this class. So I'm telling the truth, right? So homework 7 is a challenge too, because you have to learn PyTorch, which it's not that bad, but if you've never done it before, there's a lot of work involved. But the other homeworks are pretty easy compared to, not easy, but they're easier, less work than this one. So if you're finished, then congratulate yourselves. You've done a great thing. So today, we are going to talk about hidden Markov models. When we left our heroes last time, they were trying to attach POS tags to text. And they were presented with some problems. What are the problems that are inherent in POS tagging? There are really two big problems that we talked about last time. Yes. So there's ambiguity. So a single word can have more than one POS tag depending on context. And what else? Yeah. So you've got the out of vocabulary problem. So some words are not going to be in your training data, so you don't know how, what tags go with them, so you've got to have some way of figuring this out. Well, HMMs give us a way of actually dealing with both of these problems to some degree. Who here is familiar with HMMs? Okay. So who here wants to give a brief definition of an HMM? Let's back up. So HMMs are hidden Markov models, right? And hidden Markov models are sort of a special case of, or related to Markov chains. What is a Markov chain? It's easier than defining a hidden Markov model. So you can think of it as a graph with states for the nodes, with edges that have probabilities associated with them. And so you can, and these probabilities are the probability of going from the first state to the second state. So these have an interesting property. They follow what's called the Markov assumption. What is the Markov assumption? Yes, yes. Could you say that louder? Because there's a big room.
It's the assumption that the probability to get to a state depends only on the state before it, and you can ignore everything before that.
Right, right. Because you just pay attention to the extent that that matters. It's encoded in the fact that you got to that state. So all that matters is that preceding state. Well, this Markov chain. The hidden part of hidden Markov models, as we'll see, is that the states corresponds to something you don't observe, to the tags in this case, the POS tags, and you're working with things that do exist, that are observed, and you're trying to decode these into tags. And so we'll see how that is done. Oops. So let's look at the problem here. So we have a sentence. Bill directed plays about English kings. Who is Bill? What? William Shakespeare. Anyway. Directed plays about English kings. Okay? So Bill could be a proper noun, a verb, or a noun. Directed could be an adjective or a verb. Plays could be a verb or a plural noun. About could be a preposition. It could be an adverb. It could be a particle. English could be an adjective or a noun. Kings could be a plural noun or a verb, as in checkers. So how do we decide which one to choose? Well, we can look at the probabilities, the frequencies at which each part of speech occurs with that word. And we get numbers like this. So for example, for Bill, it's a proper noun 41 times in our corpus, a verb 2 times, and a noun 303 times. So it has an 87% chance of being a noun, much smaller chance of being a verb or a proper noun. Which is interesting because in this case, what is the right part of speech? Or the right part of speech tag? Proper noun. Even though this is not the most common, if we just count out the and go by the numbers. So we get similar numbers for the other words, for the different parts of speech. And one thing that we can do that we mentioned last time is we could just pick the most frequent, the most probable part of speech, and we would be right in most of the cases. Now, some cases like Bill, we would be wrong, but we would more often than not be right. Probably looks like about 90% of the time on the Penn Treebank, which is an English corpus annotated syntactically. So as we look at the other words in the sentence, we see the same thing. So English can be either an adjective or a noun. Apparently, it's a noun more often than an adjective in this corpus. And kings can be a plural noun or a verb. But it's very rarely a verb. This is only in like checkers. Anybody here ever played checkers? Yeah. So to king is like kingy. And it would have to be it would only be the third singular non-past uses of that word that would be a verb here. So well, so this is the problem space. This is what we have access to. We can get all of this information if we have an annotated corpus. We have a corpus with part of speech labeled that we can train on. Then we can know all of these probabilities, and we can be very happy. And then we can train a hidden Markov model. And this is what a hidden Markov model consists of. So you have a start state that we'll call Q0, just like in FSTs. You know, there's a start state. This doesn't have, the other states will have something associated with them, like a tag or a word. But this doesn't have anything, it's silent. And the same thing is the final state, QF, it's silent. Then we have a set of normal states, Q, which excludes Q0 and QF, which is in this cloud here. And you have a vocabulary of observable symbols. For our purposes, those are the words. For the part of speech tagging case. But they could be other things as well, depending on what you're using HMMs for. And then you have two kinds of probabilities. You have transition probabilities, gamma. So gamma ij is the probability of transitioning to qj given the current state qi. And you have emission probabilities. So eta, we're going to use gamma and eta for transition probabilities and emission probabilities. Sometimes if you read other, I think in your textbook probably, at least in the third edition of your textbook that's available online, they use A and B respectively for the transitional and emission probabilities. So just be aware of that, like if you're trying to compare pseudocode, as I was frantically prior to this lecture, then you'll know there's some differences in notation. So HMMs work like the noisy channel model. And what doesn't work like the noisy channel model? Yes? It's just a single state in an HMM. You have a single start state and a single final state. Right, right. So an HMM is works like the noisy channel model. So like other things that we apply the noisy channel model to, you're multiplying two probabilities. You're looking at the product of two probabilities. This one here, which is your transition probabilities, gamma. So that's the same as like a language model. You know, it's giving you the probability of a sequence, basically, but in the form of the probability of transition within a sequence. And then you have what is equivalent to the channel model, which is your emission probabilities. These are the probabilities that we were looking at just barely when we were thinking about how probable it was for, not exactly the probabilities, it's turned around the other way, but the probability that a proper noun is billed. You know, this would be an emission probability. And so that's what the probability of x given y in our Bayesian worldview is, whereas the probability of y, that's the transition probabilities. So emission probabilities, transition probabilities. And so the idea that to imagine in your head is that when you're producing language, really you're producing a bunch of tags, a sequence of tags. But then you're encoding this sequence in words. You're hiding your true intent, the true syntactic structure of speech. And so our task when we're doing part of speech tagging is to decode these words back into tags, to recover the hidden tags, the hidden markup model, that sit behind these words. Questions about that? So now we get to some slides that I did not make. I don't fully appreciate. But you should know that tags are not the same thing as states. But there's a relationship between tags and states. So if we have a sequence like this, Bill directed plays about English kings, then we can look and see, so these are start symbols, start tags. So we add those to the beginning of of the sequence that we want to tag for both words and for tags to give us an offset and let us know that we're at the beginning of a sequence. So it turns out that the probability of a proper noun after two start tags is much greater than the probability of a verb or of a noun, in our corpus at least. But we can extend things on down. So if you have the probability of a proper noun here, of a verb here, and a noun here initially, then we also can look at the probability of an adjective or verb following start symbol and proper noun, or start symbol and, or verb following start symbol and proper noun. So by the way, what does this look like? Yes. Yes. Just there being a proper noun. Just there being a proper noun. So we're stating these probabilities purely in terms of the tag. So in other words, what kind of probabilities are we stating? So these are really our transition probabilities, right? The probability of transitioning between states, and each state here corresponds to it's aligned with a tag. And so we're talking about the probability of traversing this sequence of tags. Does that make sense? Yeah. So when we multiply everything together for these two words, then we get some other probabilities. What does this look like that you've seen before? Like n-gram models, right? It looks like a language model. And that's really effectively what it is a kind of language model. That's why we can put it here. Well, we can just keep going. And we can calculate lots of numbers. Lots of numbers that I don't know what to say about. So we can go the other direction. We can say the probability of T, proper noun, verb, or noun, given Bill, and the probability of Bill given T. Now, which of these, what is this going to correspond to? Yeah. So given a proper noun, or given Bill, what is the probability that it's a proper noun? Or given a proper noun, what is the probability that it's Bill? So what kinds of probabilities are we talking about here? About what? Then these are the probabilities of the omission probabilities, right? I mean, that's what we're getting to. You know, the probability that relates part of speech, a hidden thing, to an observed thing, the word. So which of these corresponds to the omission probability? So the second one. So similarly with directed, it could be an adjective, but the probability of directed given adjective is basically 0, whereas the probability of directed given a verb tag is non-zero. Likewise with plays. So we see that the probability of a verb emitting plays is higher than the probability of plural noun emitting plays. And the probability of, yeah. So the probability of y here is our language model that corresponds to our transition probability. The posterior probability of x given y is the probability of the observation. So x is going to be an observable, and y is going to be the hidden state, the hidden tag in our case. So we can use Bayes' rule to put these together. Argmax it, drop the denominator, and we've got something that's fairly easy to work with. So this brings us back to the noisy channel model. So again, we have probability of y as our what probabilities? I heard it. Transition probabilities. Probability of x given y as our emission probabilities, and so we assume that underlyingly there are a bunch of tags. They're being converted by nasty humans into words, and we're going to do what? We're going to decode. We're going to decode those words back into tags. So the tagging task is to take as input a sequence of word tokens, x, and output a sequence of part of speech tags, y, one per word. So in HMM terms, this means find the most likely tag sequence given the word sequence. So if I knew the state sequence for words x1 to xn minus 1, then I could figure out the last state, right? That decision would just really depend on n minus 1. And that's what this fancy math here shows. Essentially, the idea is this is a Markovian process. And that the Markov assumption is applicable. So I don't know that sequence, right, to start off with. But there are only Q options, or cardinality of Q options, for n minus 1. And so if I can get everything up to n minus 1, then I can get n. Well, that means that if I can get everything up to n minus 2, I can get n minus 1, and then I can get n. And following that recursive logic, you can solve the whole decoding problem. You see how this works? Have some vague idea? I also have some vague idea. So you can, the most elegant statement of the algorithm that we use to do this decoding, called the Viterbi algorithm, is in terms of these nice recursive equations. So what are they saying? So we have this matrix V, and it has basically time steps in the columns and states in the rows. And we set the initial time step for the initial state to 1. And then we define recursively the values of each of the other cells in the matrix. That's this step here. So you're trying to find the max for every state in Q, including Q0, of the previous time steps, like the previous columns of that row for the previous column, times the transition probability from I to J times the emission probability for that word, for the word. So X here is the sequence of words. X sub t is that the observed word in that position, at that time step. So from state J. So given this definition, then you know all of the paths and everything. You can just find the best one. And that's what this does. So goal, you're finding the cell in the matrix, the max that is largest when multiplied by the transitional probability here from I to the final state, from state I to the final state. So you're looking at which one at the end gives you the best path to the end, to the final state. Does this make sense? it's a little bit like, I don't know. I always find it a little bit hard to trust myself when it comes to algorithms. Like I think I kind of get that. I get how that works. But when it comes to actually implementing it, I stare like closely at the pseudocode and like um, forget that I ever had any insight at all into how the algorithm actually works. Um, and I feel like having it stated in these equations makes it a little bit easier. We're going to now look at a pseudocode version of one implementation, one way of doing the Viterbi. So, but before that, let's think about this a little bit. So we could just implement something like this directly, right? It's a recursive function. Would we want to do that? Would that be a good idea? No, why not? No, you can, but you can reason about recursive functions so well. You don't have to. Anyway, they're so beautiful. Um, yeah, yeah. You keep recomputing the same thing over and over again. It's just like with what other problems have we looked at that's like this? Edit distance. It's just like edit distance. So you you can write a recursive implementation of Levenshtein distance, but it's very slow because you recompute the same values over and over again. So what will we do instead? What did we do in the case of edit distance? What was our friend? Dynamic programming. And we're going to use a dynamic programming algorithm to calculate, to implement our implementation of Viterbi. So this takes these equations and translates them uh, into dynamic programming. So we start off by initializing a matrix n by n with all zeros, and then we set the zeroth row, zeroth column to 1. So starting place. And then for every time step, t, up to n, we do this. We, for each q1, for each qj, for each qi, so we're going through all of the states kind of in both dimensions, or we're looking at the all pairwise all pairings of states within the matrix. So we set the cell TQJ to be the max of TQJ. So if it's high, then it might stay the same. Otherwise, it's going to be the value in t minus 1 qi. So looking back one step in time and at the other state times the transition probabilities from I to j times the emission probability for state I and the observed word at that time step. So that takes care of these, right? So that leaves us with this. So here we're going to just go through the states once, one at a time. And we're going to look at we're going to try to find the cell with the maximum value of um, uh, the the cell for which um, that cell times by multiplied by the transition probability to the final state is higher. And that's what we return. So who wants to explain this back to me? Who can give an intuitive explanation of what is happening here? Claire? Okay.
Step one, make sure you have all your data in the row. Step two, build an array.
So it's t times the number of states. T times the cardinality of t plus 2.
Okay, so n times, and then go down the time step, and start, and for each pair of states, for each state, the probability we're there at that time step is the max of the probability that we were already at that state, or the probability that we were at another state and we got here from the previous time step.
Correct.
And then at the very end, we have reached time step n, and so we just go through all of the states and we pick the one that we're most likely to be at.
Yeah.
Did we do that?
I think that's basically right. Anyone else want to try? So we expect you to know this algorithm actually for a midterm exam. So it's not unlikely to show up in some way on the midterm exam or perhaps even the finals. So we want you to, it's important to us that you understand it and you understand how to apply it and what it means conceptually. Somebody else wants to try to explain it in their own words. I promise to be very encouraging. Yes. Right. Uh-huh. Right, right, right. So I do not know what this slide is supposed to mean. So what about unknown words? Well, we can look actually at what the part of speech distribution of out of vocabulary words is. So we can treat out of vocabulary words as things, as separate, as a separate token. And we can estimate this from corpora. They're less likely to be closed class items than to be open class items. You can also do something, add some features basically to help us out. So beyond just looking at the raw probability, which still is pretty good actually. We can look at morphology, for example, and at orthography. So if it starts with a capital letter, more likely to be a proper noun. If it contains a number, likely to be garbage. If it ends in ed or ing, likely to be a verb or a gerund pronoun. So what if you're doing this in other languages? Well, it can be done. It's done all the time. You need lots of labeled data. And that's one thing that is an obstacle to building part-of-speech taggers uh, um, for other languages is that there's not necessarily the volume of data available that you would need to train a really good HMM. Although HMMs are pretty data, you can train an HMM, a reasonable HMM, on a smaller amount of data than some other kinds of models. So it's not a huge obstacle, but it's one that you have to think about. HMMs are, and other kinds of sequence labeling models that we'll talk about they're supervised, so you need labeled data. There's also the issue with morphologically rich languages. So this introduces sparsity into the data because lots of words, words have lots of different forms, and some of them don't occur very often. But so you need to do something like parse the words into morphemes or into some kind of morphological units, and then do the tagging on those units. So this is what you would do, for example, if you're doing POS tagging for Korean or for Turkish. So morphologically rich means you have more prefixes and suffixes than average in a language. So, well, you have more, if people really mean you have more prefixes and suffixes than English, which is most languages, except Chinese. Okay. Yeah. Right. Suffixes. Well, you actually have to break off the suffixes, or at least probably break the suffixes into groups and treat those as tokens, like as observed words. And then you could be tagging on everything as if those were separate words, rather than assigning single tags for the whole big monster word. It's possible to do POS tagging without training data, but it doesn't work very well. So there are various unsupervised approaches to POS tagging. This describes one kind of naive approach to this. There are somewhat better approaches to unsupervised POS tagging, but they amount to this sort of thing. The problem with unsupervised POS tagging is it doesn't tell you the label for the parts of speech. They're just essentially clustering algorithms. So it tells you which words go together in one category to some extent, but it doesn't tell you what category it is. It doesn't tell you that's a noun, or that's a proper noun, or that's a verb. So Brown clustering is one clustering technique that's used to do things sort of like this. It gives you more semantic than syntactic clusters, though. So Shanghai and Beijing and London are all likely to fall into the same class because they have very similar distributions. And that's what Brown clustering basically captures. So it's a kind of agglomerative, hierarchical agglomerative classifier that gives you a binary tree, and then you can pick different nodes in that tree, and that defines some category in some way. Works really well for getting semantically similar words together. Doesn't work as well for getting syntactically similar words together, which is what we're primarily interested in part of speech tagging. So this is just kind of an overview. So different different tag sets are different. So we looked before at the Google Universal tag set. There were 17 tags. On the other hand, for ChenTreeBank, which you may have read about if you read the book, there are 54, above 50 different tags. And if you think about it, ChenTreeBank is just for English. And Google Universal tag sets are for every language. So you'd think that there would be more in Google Universal tag sets because there are more different possibilities. But actually, they wanted to do things so that they were comparable across languages. And that was easier if you have more coarse-grained categories. So which way is right? Well, the answer is sort of down here. Use what is best for your task. Use what is best for your task. And use what is available. So you choose, you make these decisions based on the task and not on some priority consideration. So any questions? Any comments? So remember HMMs from this lecture, that will come back on exams and so on and on a homework. And so will Viterbi, although we'll give you an implementation of Viterbi to use on the homework. So you don't have to implement it yourself. You probably have to change the implementation to handle a different kind of basically a trigram versus bigram situation. Okay, so have fun with your homework in the remaining hours and get ready for another fun homework coming to you around midnight. It never stops.
Just